Hey there, I'm Dylan Trieger.
And I'm Ribbo Gupta.
Today we are going to present a silicon bilayer model to investigate the mechanics of the cortical folding that occurs in the brains of mammals.
The mammalian brain exhibits typical folding during normal development, forming a pattern of bumps and crevices along the surface of the brain known as gyri and sulci. The amount of folding per unit length that occurs in the brain can be quantified using a ratio known as the gyrification index. While it's debated whether one's gyrification index can be a predictor of qualities such as intelligence, we do know the amount of gyrification for a species should fall within a specific range.
When the brain folds too much or too little, an individual may suffer from intellectual disability and a host of other development-related issues in conditions such as polymicrogyria, a brain with too many folds in a thin cortex, and lyssencephaly, a smooth brain with a thick cortex.
Two major theories seek to explain brain folding. Differential cortical growth postulates that the unaligned growth rates between the cortex and subcortex cause instability and subsequent buckling. Axonal tension theory states that the tension due to the interconnectivity between axons in the subcortex pulls the neuron cell bodies in the cortex together. We build upon principles from the differential cortical growth theory to make our model.
Inspired by work done by Dr. Kuhl and the Biomechanical Engineering Department at Stanford University, we decided to create silicon bilayers with films of various thicknesses to model brain folding. Our bilayer consisted of two silicon rubbers with a Young's modulus ratio of 4.7 to 1 between the film and the substrate. The substrate was pre-stretched prior to pouring the film on top, so the elastic rebound from the substrate exerted a force on the film to compress and fold it. As you can see at the extremes, a thinner film results in a more substantial folding than a thicker film.
The film and substrate were made using compounds called Moldstar 20T and Ecoflex 0030. Both of these rubbers were shipped as a pair of bottles containing viscous, clear liquids that needed to be mixed and cured to set as solids. We used silicon pigments to dye the Moldstar 20T different colors so that we could distinguish between the films of varying thickness in our experiment.
To prepare our bilayers, we first molded a set of 8 uniform rectangles of Ecoflex 0030 and dyed them white. To ensure equal thickness, we used a tool with marked depths to measure the pore level. Each rectangle was mounted on a custom-made stretching device using C-clamps. From their initial length of 3 inches, each rectangle was stretched to 5.5 inches, just under 2 times longer. This pre-stretch exerted a compressive force on the film when released, inducing folding.
A second mold made of foam core and with various pore levels marked was used to mold the Moldstar 20T film on the pre-stretched substrate. After retrieving and trimming the final products, we were left with 8 iterations of silicon bilayers with varied film thicknesses.
This is a video demonstrating the wrinkling caused by the release of the pre-stretch.
We just want to briefly showcase the equations used to derive the experimentally determined critical wavelength as well as the analytical model for doing so. Our analytical model is based on the Allen sandwich panel model.
Our experiment consisted of 8 trials, ranging from 2 to 4 millimeters in thickness, which represents the range of cortical thicknesses found in humans. In general, as thickness increased, so did the observed amplitude and wavelength.
As you can see from our results, the critical wavelength was directly proportional to film thickness. One thing worth noting was our experimental values for critical wavelength were systematically shifted down from our analytical values.
Here, we see our results compared to a similar experiment run by Kuhl et al. Their model, which had a 4 times greater stiffness ratio, lined up well with the analytical model. In contrast, our results presented a systematic shift. We believe that the analytical model may not hold true for thicker films and low stiffness ratios. It's also possible that the experimental model is less accurate at high thicknesses, leading to inaccurate values.
The main limitation of this study was the low number of trials used. This reduced our ability to test the role of other parameters. In the future, we recommend teams study the compounded effects of varying multiple parameters simultaneously to better understand the dynamics at play. We also recommend all future trials be conducted in a laboratory to allow for increased control and access to higher accuracy instruments to measure values.
Thanks for watching!